Is there any way that the speaker can unmute? Thank you.
Okay, how about now? Can you guys hear me?
It's fantastic. Thank you so much.
It's working. Okay, great. Okay, so I guess, yeah, just to recap briefly. So, yeah, I do work in a number of areas, but mostly machine learning as well as natural language processing. I'll talk mostly today about reinforcement learning and inverse constraint learning. And then in terms of applications, it will be mostly autonomous driving and CO2 recycling, but I'm open to talk about these other applications too. And then the research I do is both theoretical and applied. So with my research group, we typically have industrial partners for every single project. And then, so I've listed here some of the industry partners that I've had a chance to collaborate with. And then, so they bring in some real problems and then data and so on. And it's really exciting. At some level, it's similar to what AI4OPT also does. Okay. All right, so let's get started. And second, this is not advancing. Okay, yeah, there we go. Okay, so I guess the menu for today is that I'll talk about inverse constraint learning. This is going to be the main topic, so I'll give you an introduction. I'll discuss two of our recent work. So I'll discuss what is the state of the art in terms of inverse constraint learning for hard constraints. You'll see that this is still a nascent research topic. The state of the art is actually not very advanced. So if anybody's interested in making contributions on something that doesn't have a huge crowd working on with super advanced techniques that require lots of compute, this would be a topic that's actually fairly open and you can make contributions. I'll tell you about some of our contributions, so in the context of soft constraints, and then after this, we'll discuss some more future work. Okay. All right, so a bit of motivation. So this work on inverse constraint learning, in fact, came from an industry partner who contacted us and said, you know, we're doing autonomous driving, and we're good at in terms of, you know, optimizing trajectories and so on based on reinforcement learning. But in order to make sure that the trajectories are satisfying various criteria, we need to include some constraints. And when we try to design them manually, it's not working out well. And then they would typically go through an iterative process of like just fine-tuning their constraints in order to obtain the behavior that they want and so on. And then they would break things in that process and so on. So it just wasn't working well. So then the question became, how can you then infer constraints from data provided by experts? So in the context of autonomous driving, all of us are experts at driving. So we drive safely, we drive in a way that's comfortable, smooth, and so on. So then the question becomes, can we infer some of those constraints and then help autonomous driving cars follow these constraints as well that otherwise are very difficult to specify manually? Okay, so in terms of background, just to make sure everyone's on the same page. So here I've got one slide that kind of summarizes what we do in reinforcement learning. So we typically have a goal. For instance, we'd like to reach some destination, and then we can specify a reward function that will essentially encode this goal. So it could just be the negative of the distance between the ego car and the destination. And then we simply come up with a policy. So we optimize a policy to maximize the discounted sum of rewards. And then so roughly speaking, you can think of reinforcement learning as a black box that takes as input, you see your objective, so the reward function. And then after that produces a policy that achieves that, right? So very simple. Now, in most real world applications, a simple objective is not good enough, especially in autonomous driving. So you would like to include all sorts of constraints to make sure that the driving style is satisfying various criteria. So for instance, here we'd like to make sure that we avoid collisions. Okay, so that might seem like an obvious thing, but then you need to include some constraints for that. And then so a simple type of constraint could just be that, let's say there's a penalty of +1 or a cost of +1 whenever the distance between the ego car and some obstacle is less than some threshold epsilon, right? So if you get too close to an obstacle, that's bad. You want to penalize this, and otherwise 0, right? So then a natural way of encoding this as part of a reinforcement learning problem is that you have your objective, you have the constraint, and here the constraints are essentially an expectation of the sum of some cost that should be less than some threshold. Okay, and this is following the framework of constraint Markov decision processes. So now you see in this framework now we take as input the rewards, we take as input the constraint, and we output a policy that satisfies that.
Pascal,
yeah.
Ask a quick question to someone on the website. Could you just talk for a little bit about like why we need the constraint function instead of just incorporating this into the reward function?
Okay, so yeah, that's a good point. So at some level, we could say that a lot of the constraint information could be captured maybe with a more complex reward function. The challenge is that with rewards, you can always trade things off. Like there might be situation where you think that a sufficiently negative reward will prevent a behavior, but then in the reinforcement learning context, maybe you just haven't seen behaviors or situations where it turns out that something else could compensate for this, and then the agent will still be willing to accept what you thought was a sufficiently negative reward, right? So then with a constraint, you can think of this as like an inductive bias where you know that something should not happen. It should be disabled, and the agent should not learn a numerical value that will be sufficient for this. It just needs to recognize that this situation now is disabled, and that's it. Okay, so I guess, yeah, it's a subtle difference, but in various applications, it turns out to be more convenient, and it gives you the right inductive bias. Okay, so now the reality is that in many reinforcement learning problem, we wish to have the reward function, the constraint functions provided by experts, but they turn out to be difficult to specify. And then so this is where there's the field of inverse reinforcement learning, where what you do is that you start from demonstrations from an optimal policy. So for instance, expert drivers, so human drivers who simply drive around, and then you observe their sequence of state action pairs, and then you try to infer from this what was the reward that they were optimizing in order to produce these trajectories. Okay, so that's the reverse problem. And then so this is essentially answering the question, for instance, given some human driving demonstrations, what rewards led to the observed trajectories? And here with what we just discussed, you could say, well, didn't we just indicate that the reward could be just the negative of the distance to the goal? So this is simplistic. In reality, there will be all sorts of situations that will not be accounted for in this fashion. And then so very often you would like to essentially refine your objective based on data that really gives you something grounded and more precise. Okay, so I guess, yeah, for most applications, once you understand the application well enough, you will realize that there's like all these edge cases, and then often a simple objective isn't going to do it, or you have trouble thinking this through. And this is where, I guess, if you have expert demonstrations, there's hope that you can learn something that's more precise. Okay, so now in the context of autonomous driving, it's in fact the constraints that tend to be much more difficult to specify, because the goals are usually easy, but then I guess the distance to obstacles that people would tend to preserve, so the gap, also making sure that the ride is smooth. These are sort of things that we do naturally, But if you ask an engineer, specify the right thresholds for these types of constraints, I actually went through the exercise myself with a simulator to try to specify the constraints. It took me several days before I could specify these constraints with the right threshold through trial and error, until in a very simple simulator, I got essentially an autonomous driving car to kind of do some trajectories that looked reasonable. And so it wasn't obvious, and this was just in a simulator. So in reality, things are more complex, and that's exactly what our industry partner was trying to get at. Okay, so I guess, yeah, in this work now we'll see how we can infer these things from data. Now, the general problem of inverse constraint reinforcement learning is that we would like to learn both the reward function and the constraints, but that tends to be very complex. Yeah.
So in this set, I have a question.
Okay.
So in this setting, everything is discretized, state, space, time, everything are treated as discrete.
No, not necessarily. So okay, here I haven't provided much detail yet, so I'm just kind of establishing some basic notation, but the states and actions will generally be continuous. Now, in most of the work with respect to reinforcement learning Markov decision processes, time will be discretized, but we can make that continuous as well. So in general, all of that is possible. Yeah. Okay. Okay, so the problem that we're going to focus on, which is a slight simplification, is that we'll assume that the reward function is given, but we're still missing the constraints. We're just going to try to learn the constraints. And yeah, the challenge is that learning both simultaneously, there are different combinations of rewards and constraints that could lead to the same behavior. So there's an unidentifiability problem. So you have to still assume enough in order to learn just one. And then so here, we're going to focus on learning just the constraints, given that we have the rewards. Okay. All right, now let me give you some intuition about the algorithms that we're going to discuss for learning the constraints. And then so let's say that we've got a simple maze problem like this. This is our starting state. We'd like to reach this goal state. And let's say that we have some expert trajectories. And I've drawn here two such expert trajectories. One of them goes like this, and then the other one goes like that. Okay, so now we would like to learn a constraint that explains essentially what we observe. And then so a lot of the algorithms, the way they will operate, and first they'll say, okay, I don't have anything to go with, so let me just try to find a path that will be optimal based on my reward. And perhaps here this will be the shortest path. So then this will lead to a first trajectory. But now you look at this trajectory, clearly it's very different from the other trajectory. So then the assumption is that this trajectory, which would normally yield higher rewards than the observed one, must have been disabled by some constraint. Otherwise, the experts would have done that too, right? So now we need to formulate a constraint that will essentially rule out this trajectory. And then so a simple thing is just to assume that this state must be blocked by something, and then this will rule out this trajectory. And if we redo the exercise, now we'll perhaps come up with this trajectory. And then again, it's different. So then we'll look for something that could prevent this trajectory. So perhaps this state, then we'll come up with this trajectory. It will be blocked again, and so on. And eventually, you see, we'll arrive at a trajectory that is similar to the observed trajectory. So a lot of the algorithms are essentially following this sort of iterative process where you alternate between finding optimal policies given your hypothesized constraint, then you observe the trajectories according to this policy, compare that to the observed ones, and then if they're very different, or at least those that are different, and if they have a higher reward, there must be something that prevents them. Otherwise, the experts would have executed them. And therefore, now we need to formulate a constraint that will do that. Okay, any questions regarding this simple intuition? Yes.
So it seems like, correct me if I'm wrong here, like when you're learning the constraints, sort of through the approach you just sort of demonstrated where you say, okay, naively, the shortest path would be to just do this, but obviously there's something preventing that. So I assume there's something, an obstacle here. You're sort of assuming that the constraint follows the format of like stay epsilon distance away from some obstacle. Is that also fed in, or are you sort of blind to, you're just trying to learn some constraint set?
Okay, so yeah, so here there's a good question about what constraint set or representation of constraints we want to consider. And in this little example, I guess what I was implicitly assuming is that constraints could just be about enabling or disabling some states, but now we're going to see that we can have a general neural network that encodes an arbitrary constraint function, and then we're simply going to learn the parameters of this neural network, and this will allow us to essentially fit some fairly flexible constraints.
Even in the finite state setting, is the constraint identification problem solved if you know the report function?
Yes, that's a very good point. So yeah, here, generally speaking, there is an unidentifiability problem. So most of the time, there will be, I guess, a lack of information with respect to certain trajectories, because whatever you observe, you know, has to be feasible, but what you don't observe could be feasible or not, and it's unclear whether there should be a constraint that prevents what has not been observed. And the assumption usually is that if it is something that is not observed and has higher reward than what has been observed, then that's a strong signal that really, if the expert did not do this and was optimal, then clearly something must have prevented that. Right? But even then in that space, it is possible to have many constraints, in fact, infinitely many constraints depending on the representation that could yield the same trajectory. So I guess, yeah, here we generally still have an unidentifiability problem. Yeah.
Question is then how do you end up giving, so how do you finally output the correct constraint out of all of these set of constraints?
So I guess, yeah, for this, ultimately, the best we can say is when we learn constraints, and we're not sure if it is correct or not, we'll simply want to see the trajectories based on a policy optimized with that constraint. How do they compare to the trajectories that are observed? And if they're similar, if they're identical, then we'll assume that our constraint is fine. It doesn't mean that it's exactly the constraint that happened in reality, but it will mean that it's an equivalent constraint. And that's usually what we're shooting for.
Yeah. But okay, from what you just said, and the way I understood your description, basically you try not to outperform the expert. I mean, if you outperform the expert, then this means something is bad, right? But you can still have trajectories with the same performance as the performance of the trajectory given, or the set of trajectories given by the expert, which are, however, violating constraints, right? In a general setting, you can have some trajectories which are forbidden, and their performance is equal to the performance of the trajectories determined by the expert, correct?
Yeah, you're absolutely right. So yeah, so if they have equal,
how do you guard against those cases?
Yeah, so this is where I guess different algorithms might look at this differently. And then yeah, that's a very good point, that yeah, with equal performance, then it's unclear what to do here, because it could just be that it's feasible and the expert just happens to have a bias towards certain trajectories, or it could be that it's actually infeasible and we don't have any information to distinguish between those two cases. So this is where normally you need to have a priori knowledge to really decide what to do. Yeah. Okay, so now let's go through some results that essentially show what is the state of the art. So in fact, with my group, we started working in this. The first thing was for us to get a sense of, how do existing algorithms perform? And then I guess what's interesting today is that there are tracks, for instance, at NeurIPS and other conferences where you can publish benchmarks, and then you don't have to have a new algorithm per se. So it's nice, when you get into a new field, you do your survey, you evaluate, and then it's already a contribution for the community about just, showing, okay, this is the state of the art. This is what the existing algorithms do. So I guess we did publish such a survey, and now I'll show you the what the results were. Okay, so now let's go into more details about one approach that is a popular approach, in part because it's also fairly simple, and it is based on the maximum entropy framework for reinforcement learning. So in maximum entropy reinforcement learning, the idea is that normally you would simply maximize the sum of the rewards, but experts often are not perfectly optimal. They will tend to select actions that have high rewards with a high probability. And this can be captured with this idea that you see what they're really optimizing perhaps is a notion of sum of rewards plus entropy of the policy. Okay, so there's a whole branch of reinforcement learning that considers this to explain essentially why agents might not be perfectly optimal. And it has some nice mathematical properties that we're going to exploit. Okay, so I guess we're going to go with this, and this leads to what are known as soft MDPs. Okay, so in that framework, what's interesting is that we don't need to necessarily have an explicit representation of the policy to look at what is the probability of a trajectory. So if I consider a trajectory, here I'm going to use tau to indicate a sequence of state action pairs, and let's say that it was generated by one of those optimal soft policy that has this entropy term, then it's possible to show that the probability of such a trajectory is essentially proportional to the exponential of the sum of the rewards. Okay, so yeah, that's the idea, that I guess the more rewards a trajectory would yield, then the higher the probability that it would be chosen. And we don't need an explicit policy representation for this. We can essentially just write down with the simple formula what is the probability of the trajectory. Now, if we have constraints, there was an extension proposed to that where all you have to do is include an additional term here. And this would be a term, let's say, for hard constraints. So this delta here, think of it as a Kronecker delta that returns 1 when the trajectory is feasible according to the constraint, and 0 otherwise. Okay, so then you see it will nullify the probability of generating that constraint if it is not feasible. Okay, so now based on this, very, very simple approach to learn constraints is essentially just to solve this optimization problem here. So we're just going to do maximum likelihood of the expert trajectories by essentially optimizing parameters of our constraint function. So here, C, which is the variable that we're optimizing, is the constraint function. So it's a function that takes as input state action pairs, returns perhaps a notion of cost, a notion of degree of infeasibility, right? And so that's what we're going to essentially learn. Okay, and then so for the case of hard constraints, then you can simply optimize this, and then you will immediately obtain a constraint function. Okay, so any questions about this? Good. Okay. So now, if we look at various problems, so what we did is we created a small benchmark where we took some classic robotics problem from OpenAI, so the AI gym, and then they all have deterministic constraints. This is the number of dimensions of observations for actions. All of these are continuous, okay? And now let's say that we impose some very, very simple constraints. So we simply want these different robots to not go over a certain threshold, let's say, according to the X coordinate, and otherwise optimize whatever is their original goal. Usually you see for half cheetah and ant and so on is to essentially just reach a destination as quickly as possible. For pendulum is to balance the pendulum and so on. Okay, so I guess we've got some simple constraints, and these are the results of existing algorithms. So what we see on the top row are the constraint violation rate. So you see these are hard constraints, and the expectation is that well, okay, so I guess for this experiment, what we did is, you see, we created some constraints ourselves. Then we got an agent to that was optimized by PPO Lagrange. So this is one of the techniques for optimizing a policy subject to a constraint. Then we got a policy and generated some trajectories. That became our data. And then we simply ask those algorithms now, can you recover the constraint that was followed by the policy obtained by PPO Lagrange? So essentially just, yeah, recover those constraints. And these were very, very simple constraints, okay? And then we can see that some of those algorithms failed completely, okay? So the violation rate, so essentially you see they learn a constraint, then we feed this back to PPO Lagrange, then we execute the policy, and then we observe, are they going to essentially satisfy the original constraint or not? And then a lot of those algorithms do not. So you see the violation rate remains high. So in this case, yeah, some algorithms simply do not find the original constraint properly. For some problems, it was pretty good. But you see, here's one problem where none of the existing algorithms were able to recover this. And here, just as a reference point, if we have the original constraint and we just want to see, is it really possible to obtain a policy that does not violate that constraint? So PPO Lagrange is such an algorithm that can take as input a constraint. Its violation rate is essentially close to 0 for most of those problems, except this one. So here it still has a 20% violation rate. And then in terms of rewards, you see it can generally obtain fairly high rewards. So like there's an important gap in some problems, meaning that these algorithms still have a way to go to find original constraints. Yeah.
So just to make sure that I understood correctly, the issue is not that the policy is not able to satisfy a constraint, is that you did not identify correctly the constraint that you wanted to satisfy.
Exactly, yes.
And can you comment on the fact that some of the algorithms, especially for block end, have higher reward than PPO Lagrange?
Yeah, so, okay, so here, in some cases, you see the violation rate was not 0. So it is normal then that they will earn some higher rewards. In some other cases, their violation rate went down to 0. So what this means now is that PPO Lagrange itself was not optimal. So these algorithms in some cases actually found something better than PPO Lagrange itself that was used to obtain a policy given the constraint. So I guess, yeah, this just shows that you see the state of the art is far from perfect. These are simple problems. I mean, there's nothing difficult really from an optimization perspective here. But yeah, they're struggling to really reliably find the constraints, or given a constraint, find the optimal policy. Yeah.
To be clear, is this the forward algorithm, or are you inferring constraints like in the inverse setting? This is just standard algorithm for constraint.
So here there's essentially both together, because what we're benchmarking is now, let's say we give trajectories, and these algorithms are asked to do the inverse problem, so find the constraint, and then after that we give them to a forward algorithm that uses the inferred constraint and produces trajectories. Then we essentially estimate, what's the amount of reward and violation rate of those resulting trajectories. So both of them together.
The plots are like after you do the inverse learning and generate trajectories. That works.
Yeah.
As you may know, I'm an optimization person, which means if you give me constraints and you tell me if these are hard constraints, and you give me a solution that doesn't satisfy the constraints, I take your solution and I throw it in the trash. It's a very, I don't think we have a settled way in optimization community to deal with things that are feasible and things that are infeasible. And so I'm wondering if you have like a systematic way of comparing on a fair basis a policy that satisfies the constraints that they're supposed to be satisfying and a policy that does not. Like, is there a way that you can sort of reconcile the two?
I would say there isn't. And I mean, the right thing to do is a bit like you said, that, if it doesn't satisfy the constraint, you put that in the trash. And so when my students showed me those results, I was like, this is clearly not working, but okay. I mean, this is the state of the art, so we report that. and that means, there's plenty of room here for the community to improve on this. So the reality is that, okay, in the reinforcement learning setting, satisfying a constraint is also challenging because you're also learning about the environment at the same time. So it's possible that what really happened here is that internally the algorithm is satisfying the constraint, at least it's thinking that it's satisfying the constraint with respect to the model that it has learned. But if that model is wrong, then as a result, it may not really be satisfying the constraint with respect to the true underlying model, right? So that's the problem. Like here, in some sense, in machine learning, we never have certainty that we have the correct model. So that's why having a validation rate that is exactly 0 is probably also too idealistic. I know from an optimization perspective, I guess, yeah, we shake our heads and it's like, this is trash, right? But here we're in a setting, you see, where we don't know the problem, and that's why it has to be learned as well.
I would be the extreme with throwing stuff in the trash, but I feel like there should be sort of a trade-off and somewhere in between. I don't think we've really nailed that down. So anything that you have on that topic, I'll be super curious to see.
Yeah. Well, okay. The other thing to realize is that hard constraints are something that's has led to a lot of debate in the community because at least in reinforcement learning, generally speaking, the environments are stochastic. So having something that operates in a stochastic environment and can guarantee that it will satisfy a hard constraint means that it will have to somehow, I guess, overcome the stochasticity of the environment to make sure it never, I guess, violates the constraints, right? And in some setting, that is mathematically impossible. That's the other thing. So this is where there's a shift in the community now towards soft constraints, because otherwise, yeah, we're working with ideal problems that are simply not realistic.
Thank you.
Yeah. Okay. Now, something a little more realistic is coming back to autonomous driving. So we took some public data sets. So there are public data sets like HID, XZD, where essentially human drivers were recorded with some drones on some German highways. And then so you have, I guess, real demonstrations from human drivers. And then you can ask, can we learn the constraints that these human drivers were following? So here, instead of learning the constraints that those drivers were following, which are unknown, we still played the game of, okay, what if we impose some constraints that we're going to specify by hand? So for instance, here, let's say we just want to have a constraint on velocity and also make sure that there's a certain distance between the cars, very, very simple constraints. And then we ask the same question, what do the state-of-the-art algorithms do? And it's not pretty again, okay? So you can see that their violation rate is not close to 0, but it is possible to obtain 0. So there are solutions that would achieve that, but they don't find that, okay? And then for the amount of rewards also, and in some cases, it's much below what could be achieved when we know the optimal solution, okay? All right, so now let's move on, and I'll tell you about some of the work that our group did, in particular by designing a technique to learn soft constraints. And part of the reason for focusing on soft constraints was because when we worked on the autonomous driving, let's say that we want to learn a constraints with respect to the gap to the car in front, then the problem is that if you gather enough data, there will be essentially near incidents where a car got so close to another car that it did not collide, but essentially the distance could be arbitrarily close to zero. And then you would effectively be learning a constraint that would say, well, I guess the distance just has to be greater than zero, but that's not interesting. That's not useful. I mean, we don't need algorithms to figure this out. What we're more interested in is, finding what's, I guess, a comfortable gap that would ensure safety. And then in other situations where we want to have comfort and smoothness as well. So, and what are the implicit constraints of human drivers in terms of acceleration to prevent jerks and sudden movements of the cars and so on. Okay, and the problem is that hard constraints are too conservative here, and would change as we increase the amount of data. So we had to go for soft constraints. Okay, so now what do I mean by a soft constraint? So I guess just to give you a concrete example, so let's say that we have 3 trajectories, tau 1, tau 2, tau 3. Let's say that their constraint values are 2, 3, and 4. If we specify a hard constraint, it would be something like the constraint value should be, let's say, less than 3. And now a policy that would generate these trajectories, because there was one trajectory that is greater than 3, we would say that it violates it. And therefore that's no good. But if on the other hand, we consider a soft constraint where we look at the expectation, so in other words, the mean of these constraint values, so here the mean is 3, that is less than or equal to 3, and that would be fine. So the idea is that you see, like with human drivers, most people tend to drive in a way that's comfortable, safe, and so on. Every once in a while, you've got people who do like near accidents or, get into some weird situations, but you don't want your constraints to necessarily be affected by these outliers. So that's why you need to have soft constraints. And here, mathematically, what's the simplest is define the constraints on the expectation as opposed to making them hard. Okay, so that's what we went with. Okay.
Also import this soft constraint using with very high probability C tau I is less than 3.
Yes. So yeah, that in fact is the most natural way of specifying a soft constraint, but at least in the literature of Markov decision processes, it's not something convenient. So we're used to maximizing expected rewards, and therefore having expected values for the constraint is something natural, and we know the mathematical machinery to work with this. So when you look at, you see the literature on constraint Markov decision processes, everything is in terms of expectation. So in this work, that's what we went with. But in fact, we are currently working on doing exactly what you're doing. But then the math becomes more complex. Okay, so that is an open question for the community. Yeah. Okay, and then for the constraint function, we're also using a neural net to essentially represent it and be able to obtain functions that are fairly general. The algorithm that we developed essentially has this loop. So we're going to have a forward phase where we do constraint policy optimization. And this part, there's nothing new at some level. We can use existing algorithms like PPO Lagrange, PPO penalty, and so on. What is interesting is now how do we adjust a constraint based on the policy that has been learned? And then so we have a constraint function adjustment step right here that essentially corresponds to this max-min optimization. Now, this approach, we were able to show mathematically that it is guaranteed to converge to the optimal policy under mild and suitable conditions. So in our paper, we've got the derivations for this. So I guess, yeah, here, otherwise, it's always interesting to ask, okay, you've got this iterative process that will each time generate a new policy and then adjust the constraint to prevent trajectories that would be too different, essentially, from the trajectories of the expert. Now, how do you know that this will really converge? So here, we were able to prove that this will converge in the limit under suitable conditions. Now, the trouble is that this optimization here is not an easy one to do because we've got a max-min problem with a constraint and so on. So then to make this more practical, we did an approximation. And the trick is that when we generate a new policy at every iteration, we're going to combine them into a single mixture policy. So the trouble is that we had several policies, and we needed to make sure that our constraint would essentially rule out all the trajectories of all those policies that were too different from the expert trajectories. But now if we can combine that into a single policy, and then one way of doing this is just create a mixture policy, then it gives us a simpler optimization problem. So here it just becomes a max. There's no max min, so just max, and then with some constraints, and we're able to solve this. Okay, so that's the approach that we developed, and I'll show you some results with different benchmarks. Okay, so just to show how the algorithm evolves in terms of learning constraints. So if we have a simple maze where it's starting at the top, it needs to reach a destination at the bottom, and then it has let's say observations of trajectories that go around a wall in the middle, then it will gradually essentially learn that there must be something blocking in the middle, and that's what we observe here. So you can see that it's still not perfect, but it gives you a sense of what the algorithm did. Now, on some more interesting problems in robotics, we have in this column here a true constraint that we imposed, then generated some data, and then got the algorithm to learn back that constraint. And we can see our algorithm essentially obtained some learned constraints that are similar to the true constraint here. The middle two columns here are previous approaches that did not work as well. So in some cases, like they're just completely off. But yeah, I guess we were able to recover a shape that's similar to the true constraint. We did the same thing with highway driving. Here, the scenario was very simple. You have a car, it's following some other car on the highway, and now you just want to learn, I guess, what's the gap that's safe to keep as a distance to the car in front. And now the gap, I guess, yeah, the gap would typically vary with the speed. So if you go at low speed, it's natural that you can leave a smaller gap. If you're driving faster, then the gap would be bigger. And so what we observe here with our algorithm is that we have in red, these are expert trajectories. So they're all feasible. And then this is a heat map here where we can see in black essentially what's considered the feasible region, and in white this would be the infeasible region. And at the boundary we can see that as the speed increases, then the gap that needs to be maintained naturally increases. And then so this was learned using a neural network, and then so it naturally found this type of relation. So we were quite happy about this. And then some of the alternative techniques did not find something that was realistic here. Okay, we've got another scenario here with lane change. So there's some interesting questions about when you do a lane change, how quickly does acceleration vary laterally? So typically you see you don't have any lateral acceleration, then you start changing lanes, so you have a bit of lateral acceleration, then you decelerate and so on. And the problem is that if you don't have any constraints about that, then you would have autonomous drivers who would like change lanes almost instantly, but that's too dangerous because the car could roll over and it would not be comfortable for passengers. So here we can see again in red the expert trajectories, and then this is as a function here of lateral velocity and also the distance to neighboring cars. And then in black, that's the feasible region. In white, that's infeasible. So algorithm did quite well in that sense, and the other algorithms were not really working. Okay, and I've got one last demo here. This is something I got from one of my students just last night. The video is not quite what I was hoping the student would produce, but I figured it's good enough to show. So essentially, what we see is that there's at the top a truck, okay, that's in the right lane. And then we've got some cars in the left lane that are going faster. And then the question is, when is it safe for the car to pass the truck? And what we see are trajectories that are considered too dangerous in red, and then trajectories that are considered safe in green. Okay, so essentially the constraint function that we learned was able to rule out these trajectories that would imply a lane change that's too quick and might lead to a collision with the truck, and then was able to keep as safe those that essentially wait long enough to keep a certain distance that matches, I guess, how humans would drive. So that's what we see in this picture. Yeah, and I'll pause for a moment to see if there are any questions about this work. Good, okay. All right, so now I guess, yeah, I'll take just a few more minutes to talk about some other interesting things that we're starting to look into. So this is ongoing work and otherwise future work. So we've got an interesting collaboration with some colleagues in chemistry to do CO2 recycling. And there we encountered again a problem of learning constraints. So I guess the setup is that a lot of the energy is often produced via fossil, I guess a combustion of fossil fuels, right? And then that produces CO2. And at the moment, most of it is just released in the atmosphere. But it turns out that the CO2 could be captured, and then it can be recycled and utilized to produce new fuels or other chemicals that are useful in various industries, or you could store it. Now, for this part here, where we would do CO2 recycling, there's an important challenge because CO2 is a very, very stable gas. And then to transform it, you do have to pay a lot in terms of energy to transform it into something else. So here, there's an opportunity for research to design a catalyst that would essentially reduce the energy barrier. And then, so one reaction that is quite promising for this is known as the reverse water shift gas reaction. It takes CO2 with hydrogen, converts it into water and CO. CO, you might say, well, that's no better than CO2, but CO is less stable and then can be used as input for all sorts of other processes. So very often when CO2 is recycled, there's an intermediate step of converting it into CO, and then after that into other things. But it's that first step of breaking the CO2 into CO or something else that is the most expensive. And then so here, the challenge is how can we reduce the energy barrier? And typically that involves designing a catalyst. And then so that's an interesting material design question. Now, this can be formulated as an optimization problem. In fact, it would often be known as a Bayesian optimization problem. So you have, let's say, the energy activation for different possible configurations. So here are different configurations. This corresponds to different catalysts or different materials. And we would like to essentially search to find the best one. So there's a combinatorial optimization problem here. But the trouble is that in theory, I guess we can use plenty of techniques for Bayesian optimization to do this, but when we were working with our colleagues, the algorithm would essentially suggest some materials. They would look at it for sometimes, 2 seconds and tell us, oh no, Pascal, this would never work. I was like, what do you mean it would never work? It's like, well, we can't synthesize this in the lab. Like this is not going to, like our processes cannot allow us to build that material. It's like, okay, fine. So like, why is this? Tell me the constraints. Why is this not possible? And this is where, we spent hours discussing, and they cannot specify the constraints. Okay, so they're researchers, they're mathematically, very adept and so on, but usually, they look at a material and they've got, I guess, their intuitions about what's possible and so on, and then they can tell us each time, yeah, this is possible, this is not, but so far we haven't been able to get a constraint out of them, okay? So I guess right now we figured, okay, this is an opportunity for research. So Bayesian optimization has already been plenty of work. There's also some work for constrained Bayesian optimization, but very little to no work for also not just learning the main objective, but also learning the constraints. So that's what we're currently working on as well. So learning constraints for that. Okay, and then the last thing I want to mention briefly that I think can be a game changer. So it's something we're just starting to work on. I was discussing with Pascal earlier that perhaps it could also serve as a way for us to collaborate on various problems. So as you've heard, I guess there's been a revolution in natural language processing with large language models, but these things are really just special cases of what are known as foundation models. And I guess the interesting thing is that historically in AI, in OR, in most fields, we would take a problem and essentially try to get as much information about this problem and exploit everything we can to solve precisely that problem. There's been a realization that in lots of fields, especially in NLP, as well as computer vision, often these techniques lack common sense, but if you pre-train some super large model, it will eventually gain that common sense, and then it can serve as a starting point. So now in some fields, especially in NLP and computer vision, you do not solve problems from scratch anymore. You always start from a foundation model that gives you a better starting point. And then after this, you essentially fine-tune the model and obtain something that's better than if you did it from scratch. Now, for our purposes, now there's a lot of interest in doing something similar for sequential decision making. And the realization is that these foundation models, including in NLP and vision, they're not just working with data, there's interaction with the environment, okay? So the idea is that the foundation model is pre-trained on lots of data, but then after that, will interact with some external entity. And then from that perspective, there's lots of other applications where we could think of designing foundation models that could be useful. So wherever there's some form of decision making, where there's a feedback loop, there's a possibility here of pre-training something that could help with notions of common sense, could give you a better starting point, and then after that would lead to just better solutions overall. So I guess autonomous driving, a lot of people are looking into this now, also robotics, but generally speaking, yeah, these are just examples. Okay, so, and also an interesting connection between reinforcement learning and large language models is all the work on what are known as decision transformers. So you can in fact view reinforcement learning as a sequence modeling problem. And then some of the early work for this was in 2021. And now you can essentially treat your sequence of state, action, rewards as like a sequence of words, and then train a large model that will predict the next thing in the sequence. And now if you condition on the amount of rewards that you want to get in the future, so if you're doing optimization and you know that you would like to have a solution that achieves a certain level, then the idea is that here you would essentially give as input to your sequence model the amount of reward that you want to achieve, and then it would condition on this and try to find sequences of actions that would lead to this. And they've been quite successful at demonstrating this in certain applications where there's already plenty of data. And in fact, in the context of autonomous driving, there's, as of this year, at least one piece of work where it was demonstrated that using such a foundation model, you can in fact beat reinforcement learning agents at, I guess, driving through unsignalized intersections. Okay, so generally speaking, you see, this whole business of foundation models, you shouldn't think that it's only applicable to computer vision and natural language processing. There are models that are multi-modal, so they've now been extended to robotics, and also task and motion planning. And the idea is that really we have these sequences of state actions, observations whenever we do sequential decision making. So then there's some possibilities to, you see, leverage a lot of that work as well to design such models. So in any case, this is something that with my group we're starting to look into. And what that would entail for us, I guess, in sequential decision making is that perhaps we could have some reference implementation that could be used for different types of applications. And then they wouldn't solve any of those applications very well, but they would be a better starting point than just from scratch. And then they could get fine-tuned to obtain better solutions overall. Okay, so let me conclude now. So I guess what I presented today are techniques for inverse constraint learning. And I guess the original motivation is that in most problems, the models that we have are wrong. We know this. Models are never perfect. They're typically wrong. And then instead, we need to start from data. So in the case where the constraints are the part that we're really uncertain about, then what I presented today are essentially techniques for learning the constraints. Now, what's both sad but an opportunity is that you saw that the state of the art is not that advanced, okay? In our case, you see, we just started contributing as well in that field. Anybody who's interested, here you see the optimization, in fact, is not even difficult here. I mean, we're looking at like really simplistic constraints, but the problems, yeah, there's plenty of scope to make progress here. And then, yeah, so I would encourage anyone interested to join that community. And then for future research, I mentioned that we're currently working on something similar for you see CO2 recycling. We're also extending this work. In fact, this is some work that just got accepted at NeurIPS, where we've got a multi-expert, multi-constrained version of this work as well. We're also looking at doing uncertainty quantification. We're looking at doing this with offline data. And then finally, we're also looking at reinforcement learning foundation models. Okay, so let me stop here and I'll be happy to take some questions. Yeah.
So in those inverse problems, so I wonder, would you be able to learn both the constraints and the reward jointly?
So there is one piece of work that attempted this. And when you do this, you do have to make some assumptions because, as I mentioned before, there are different combinations of rewards and constraints that could explain the same behavior. And unless you don't care about what's the combination, if you do care about what the constraints are going to look like or the rewards are going to look like, then you have to make some assumptions to restrict the space.
Cool. Just a question. I'm just curious about your industry partners. So were they able to implement things and interpret the results to their match some of their engineering criteria?
Sorry, I guess there was a bit of noise. Can you repeat?
I'm just curious if this work has been implemented with your industry partners. Were they able to implement them and give them some constraints and interpret them within their framework?
Yeah, so okay, so for instance, well, the work that I presented for inverse constraint learning for autonomous driving, that is done with an industry partner. And then so for instance, there, because we don't know what are the true underlying constraints, like people just drive, but I mean, nobody told them follow this constraint, they're just driving. So for this, this is where we're struggling to demonstrate that we have constraints that make sense. And then so for instance, this little video here was one example of some demonstrations that my student just produced last night for our industry partner. But I guess we have to improve, I guess, the visuals of this to convey that. And the tricky part is our industry partners, the decision makers are not well versed in reinforcement learning, optimization, or anything like this. They're business people, so we have to convince them that this is working.
By using read and graph, you lose a significant portion of your audience.
Okay. Yeah.
Are there any ways, generally, not only this context, but generally, Are there ways to certify the quality of the data? Because in your last slide, you said all models are known. You have to go to the data. But how do we know that the data are really good? Because that was a key issue for your presentation.
Yeah, that's a very good point too. So I guess to do this work, for instance, we took this data that